Good afternoon. Linear algebra. This will probably be our last video. We have a couple of things we have to do here. Why don't we get right down to it? So what is this going to be about? We have a couple of things we're doing here today. Number one, we're going to have fun. We're going to have fun with trig. Oh boy, I know you can't wait. And then the second thing that we need to do here is we need to talk about this thing that is called the dot product. Or sometimes it's referred to as the scalar product. And then after that, we can start doing some information retrieval. So why don't we start off with fun with trig. So you all remember trig. There was this wonderful thing called sine, and there was this other thing called cosine, and there was this other thing called tangent. And you may remember if we had a right triangle. So here's a right triangle right over here. Okay, right means that there's a 90 degree over here. This thing over here was called the hypotenuse. Over here, there is an angle theta, like that. And maybe going back to high school or maybe in college, you learned a couple of things over here. You learned that sine theta was equal to the opposite over the hypotenuse. Remember, the hypotenuse is this one. So if this is theta, that would be this over, let's call this, why don't we call this A, and why don't we call this B, and call that H. So this would be the opposite, which would be A over H. And cosine of theta was equal to the, actually, I've made a mistake here already. This, I said opposite, but I called it A. Okay, over here, cosine would be the adjacent over the hypotenuse, which in this case over here would be B over H. And then tangent of theta, that is equal to the opposite over the adjacent, okay, which would equal A over B, which, by the way, is also equal to, you probably remember this identity from a long time ago, that's sine theta over cosine theta. Okay? So that's one way to think about these trig functions. I have a different way that I prefer to think about them, and perhaps you've all seen this too, that if you come over here and let's draw our XY plane. See, here is the Y plane. Over here is the X plane. And I could probably do something very clever here. I'm going to try it at least. Actually, I'm not. I'm going to come over here and I'm going to draw what I call the unit circle. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Let's see how well I draw a circle. So there's a circle. And what I want to assume is that this is the unit circle. So in fact, if I come over here, this is the point 1, 0. Up here is the point 0, 1. Over here is, that would be minus 1, 0. Over here would be 0, minus 1. And I want to make pretend that over here, I've drawn a line, and over here is some angle theta, like that. And again, what we can do is we can imagine that we consider two lines here. And I'm going to draw a dotted line coming down here onto the x-axis, and I'm going to draw another dotted line here which is going on to the y-axis. And the thing to keep in mind here is in this situation here, since this is the unit circle, the distance from here to here, okay, whatever, no matter what the angle theta is, this is 1. So if I come over here and I were to say, well, what is sine of theta? Well, remember, sine of theta is the opposite over the hypotenuse, okay? And in this case, the hypotenuse is 1, so this is just equal to the opposite. Okay, so the opposite of this thing is this length right here, okay? And the question is what is this length? Well, if I project it over to the y-axis, it's just this thing right over there. So that this is in fact just equal to the projection onto the y-axis. Likewise, if I were to come over here and I were to say to you, well, what is cosine of theta? Well, cosine of theta is equal to the adjacent over the hypotenuse, but in this case, it's just going to be the adjacent, okay? And if I come over here, that is just going to be equal to this length over here, okay, between here and here. In other words, I take this point here and I project it onto the x-axis. This is equal to projection onto the x-axis. So again, you can imagine, if I come over here, if here's the origin, and if this is 1, then if I come down to here, to this point here, this distance from here to here is just the cosine of theta, where theta is the angle right in there. If I were to come over here and this thing would be going way up here like that, and again, here's theta, I look at the projection onto the x-axis, and I can see this over here, this little distance here, that's cosine theta. So there are a couple of things that you should keep in mind here. That if I am looking at, suppose theta is very small. If theta is very small, that means I'm going to have something like that. And you can see that as theta is very small, the projection onto here is going to be close to 1. So basically, I want to make the following statement. For small theta, cosine theta approaches 1. And the other thing that I want you to note is that, okay, as theta approaches 90 degrees, okay, cosine theta approaches 0. We can see over here, for example, if we're projecting just up to here, here's cosine theta, and you can see that as this angle is getting bigger, this is going to be getting smaller. So let me just save this. Again, going back a very long time ago, if you came over here, if this is pi over 2, 90 degrees. If this is pi, if this is 3 pi over 2, and this is 2 pi, over here at 0, the cosine of 0 is 1. Okay? And what happens is as we get to pi over 2, it's coming down here like this. And believe it or not, I mean, we could have fun here. Um, we know that it's going to come down to here, and then it comes up to here, and then it comes back up to here, and then it starts to repeat itself. But in fact, this is the only part that we're going to be worrying about. This is just between 0 and pi over 2. So that's it for trig. All done. Almost. Now, I want to talk about something called the dot product. And the dot product is something like the following. The dot product says, suppose you're given two vectors. So suppose I've got v, which is 2, 3. And let's suppose I've got a vector w, which is equal to 4, 2. There's something called the dot product v dot w, like that. And what that is equal to, and there are going to be two definitions for it, so I'll give you the easy one first. So the easy one says what this is equal to is it's equal to 2 times 4 plus 3 times 2. In other words, what I do is I multiply these two numbers together, and then what I do is I add these two numbers together. And in this case over here, it's equal to 8 plus 6 is equal to 14. Okay? That's pretty easy. We can extend this to higher dimensions if we wanted to. For example, if v is equal to v1, v2, v3, v4, v5, and w is equal to w1, w2, w3, w4, w5, then v dot w is equal to v1 w1 plus v2 w2 and just so that you all don't get scared, you should get used to this notation. That's the summation from I goes from 1 to 5 vi w sub I. That is called the dot product. Now there is a different definition of the dot product, and it turns out to be completely equivalent, that v dot w dot product, this is equal to the length of the v vector times the length of the w vector times the cosine of the angle between v and w. Well, let's play with that a little bit. I'm not going to prove that these definitions are equivalent, but let's look at a couple of examples and maybe we can convince ourselves that they give us the same thing. So why don't we come over here and let's consider the following. So let's come over here and why don't we have this vector v is equal to 2, 2. Okay, let's let the vector w, why don't we let that be 3, 0. So 1, 2, 3, here would be w. So here's V, here's W. Okay, now for example here, if I come over here and I go V dot W, well, that's equal to 2 times 3 plus 2 times 0, and that's equal to 6. Okay, I hope everyone sees that. Now, let's come over here and let's calculate the length of V. Well, the length of V would be 2 squared plus 2 squared, and we take the square root of that, so that's equal to the square root of 8. The length of W, well, that's just equal to the square root of 3 squared plus 0 squared, and that's just equal to 3. And now we can see over here the angle theta right there. Well, we can see that theta is equal to 45 degrees. Okay, by the way, 45 degrees, if you remember radians, that's pi over 4. So the question is what is the cosine of pi over 4? Well, remember, if I've got a 45, 45, 90 degree triangle like that, let's see, it's 1, 1, and this would be radical 2. And if this is theta over here, and the cosine is the adjacent over the hypotenuse, that's equal to 1 over radical 2. So now I get that V dot W is equal to the magnitude of V times the magnitude of W times the cosine of theta. Well, the magnitude of V is radical 8. The magnitude of W is 3. And the cosine of theta is 1 over radical 2. Well, first of all, so this is equal to radical 8 over radical 2 times 3, or this is actually equal to radical 8 over 2 times 3. 8 over 2 is 4. Radical 4 is 2. 2 times 3 is equal to 6. So we can see that that number equals that number over there. So again, what I want to emphasize here that V dot W is equal to the magnitude of V times the magnitude of W times the cosine of theta, where theta is the angle in between them. By the way, if V and W are normalized, remember what that means. That means that the lengths of each one of these is 1. Then I get that V dot W is just equal to the cosine of theta. Now another thing, and this is where we're going with this, this is what we're going to be doing a lot of once we start doing some real information retrieval here. We get from this that theta is equal to cosine inverse of V dot W. Or if they're not normalized, it is going to be V dot W over the magnitude of V times the magnitude of W. We're going to be looking at this quantity a lot. Now this is a quantity. This is always between 0 and 1 for the things that we're going to be looking at. Well, what does it mean if it's really close to 1? If it's really close to 1, that means the angle between V and W is very small. It's almost 0. Like it might be 1 degree or a half a degree or 5 degrees. On the other hand, if the number is closer to 0, that indicates that the angle between these two vectors is getting very close to 90 degrees, or pi over 2. And that is the key point that we need to keep in mind here. Okay? We're going to be looking at these, and believe it or not, these vectors are going to correspond to documents that we're looking at in our database. And how we make documents into vectors is really, really, really cool. But then when we make them into vectors, then we're going to be able to calculate the dot product between them and look at this quantity here. And that's how we can decide how similar documents are to each other. This is very important. So I'm going to write important with capital letters. And what you should do is you should go back and review this particular video and make sure that you understand it.